Good afternoon to all of you. I am Rama Krishna from Keele University, delivering the series of lectures on heat transfer. In the last class we have seen the extended surfaces or fins, and this lesson is continuation of that extended surfaces. Before going to this today's session, let us review what we have covered in the last class. The convective heat transfer is given by the relation Q equal to HAS into delta T, and if you want to improve the heat transfer by means of convection, either you have to increase the value of H or surface area, because delta T you can't increase, Ts minus T alpha. T alpha is always constant. Objectivity of improving the heat transfer from the surface is to reduce the Ts, hence we can't touch this delta T. H is a complicated one which will be decided by the capacity of the surrounding fluid. So we have very limited chances to improve this H. So what is best thing is to improve the surface area. The surface area for convection can be improved by increasing or by adding a additional surface to the base material, or by extending the original surface, and that part is called fin. So fins are basically meant for improving the rate of heat transfer. And we have seen the governing equation for a fin of uniform cross-sectional area is theta equal to C1 e power mx plus C2 e power minus mx, where theta is the temperature difference between the fin surface and surroundings at any point x along the length of the fin. And m is a parameter which is equal to square root of Hp by Ka. H is the convective heat transfer coefficient, P is the perimeter, K is the thermal conductivity of the fin material, and A is the cross-sectional area of the fin. So the equation theta equal to C1 e power mx plus C2 e power minus mx is the general governing equation for fin of uniform cross-section under one-dimensional steady state heat conduction, assuming thermal conductivity is also a constant, not varies with respect to temperature. With these assumptions, by considering both combined and conduction and convection along the length of the fin, we have derived this expression. And to determine the C1 and C2, two constants involved in this equation, we need to specify two boundary conditions. One boundary condition we have identified is at x equal to 0, that is at the beginning of the fin, the temperature is equal to base temperature. A data will be given to you, or theta equal to theta naught. But the second boundary condition depends on different cases. So we have resolved three cases. One is a case of infinite long, the second one is a fin with end insulated, and the third one is a general case. Infinite long fin. No fin will be of infinite length, because as we move along the length of the fin, after some length the temperature difference decreases and the end portion of the fin may not be able to effectively convect heat into the environment. That portion is additional weight on the system, occupying more space, increasing the cost, and other problems it will create with reference to the feasibility of the system operation. So therefore, unnecessarily nobody will go for a fin of too long or infinite length. But anyhow, this is an assumption. This is an assumption which we will consider when the length by diameter ratio or length by thickness ratio of a fin is very high, maybe greater than 20 or like that. So under such condition, we will get the second boundary condition as at x is equal to L, as L tending to infinity, the temperature of the fin at the end is equal to that of surrounding temperature. So using these two boundary conditions, you can solve this C1 and C2, and we got the temperature distribution equation theta by theta naught equal to e power minus mx. From that, we have derived the expression for heat transfer equal to root of Hp Ka into theta naught. As I said, no fin is of infinite length, so this is a very remote assumption, crude assumption rather, which is not at all practically feasible. So let us take the second assumption, fin with end insulated. No fin again will be insulated at the end, but if you take the end dimensions of the fin, in case of a circular fin it is pi by 4 d square, or in case of a rectangular fin it is w into t, because the fin diameter is very small, maybe in mm, or even w and t are also in mm. The fin end area will be in the order of 10 to the power minus 6 meters square, which is very, very small. Hence, even though it has got convection from the end, it is very small and hence can be treated as 0. In such a case, the fin can be considered as fin with end insulated. So the other boundary condition you will get when you assume the case fin with end insulated, that is at x equal to L, that is at the end of the fin, because it is insulated, there is no heat transfer, hence minus Ka dt by dx at x equal to L equal to 0, which means dt by dx at x equal to L equal to 0. By applying the two boundary conditions, you can solve for the temperature distribution equation as theta by theta naught equal to cosh, hyperbolic cos m into L minus x by cosh ml. And similarly, the rate of heat transfer is given by root Hp Ka theta naught into tan hyperbolic ml. So this is the second case. And third case is general case where we don't take any assumption. The end heat transfer from the fin face at the x equal to L, whatever passes through that last element by means of conduction ultimately enters into the environment by means of convection. So the second boundary condition for a general case can be written as minus Ka dt by dx at x equal to L, that is conduction heat transfer at the end x equal to L, is equal to HA delta T at x equal to L. The convective heat transfer to the environment at the end of this. So these are the three cases, and in this third case the rate of heat transfer Q is given by root of Hp Ka theta naught into sin ml plus h by mk cosh ml by cosh ml plus h by mk sin ml. So temperature distribution equations, heat equations in all the three cases are derived. Now, when you consider a general case, the equations to determine either temperature distribution or heat transfer are tedious. And in general, no fin is of infinite length. So most possibly, a fin with endly insulated case will fit into a original one because the end surface area is very, very small. It is almost as if the fin is with end insulated, even in general case also. With that criteria, what we will do is, we will consider a fin with end insulated, but the end heat transfer maybe sometimes is not so small to neglect it. Hence what we will do is, we will slightly extend the length of the fin such that from that extended portion of the length, the rate of heat transfer will be exactly equal to the heat transfer from the end face of the fin. So by increasing the length, you are compensating the end heat transfer from its face. Now you can treat it as a fin with end insulated. How much length I have to extend to take a general case as fin with end insulated? That is, the corrected length LC is equal to L plus delta L, where delta L divided by perimeter. So that the end cross section, whatever it is conducting into the environment, is compensated by increasing the delta L into perimeter, that surface area, increasing the surface area. Therefore, these two will compensate. You will get delta L equal to AC by. So by extending the length by delta L, a general problem can be treated as a fin with end insulated, the easiest way of solving a complicated fin problem. Now in this we have introduced a non-dimensional number called Biot number. And Biot number is nothing but the resistance offered internally within the body for heat transfer, that is for conduction, and to that of resistance offered externally for convection. So internal resistance is conduction resistance, and external resistance offered for the body to exhibit, to dissipate heat into the environment is convection resistance. So L by Ka by 1 by Ha. But A here is cross-sectional area and this area is surface area, and hence what we will do is we define LC as characteristic length, and hence you will get Biot number equal to HLC by Ka or HL by K. Now the efficiency of the fin is defined as the actual heat transfer from the fin divided by ideal heat transfer. Ideal heat transfer is the maximum possible heat transfer. When the heat transfer will be maximum? Only when the entire fin is at its base temperature. So when the entire fin is at its base temperature, the heat transfer is maximum and is given by the formula H into total surface area into T naught minus T alpha, because we are assuming that the entire fin is at base temperature T naught, the rate of heat transfer is maximum. In practice, as we proceed along the length, we know that the temperature will not be constant. It drops from T naught and tends towards T alpha. So this is an ideal case. Now Q actual is equal to efficiency into Q ideal. Now the formula for efficiency we have derived as tan hyperbolic ml by ml. So if you correct the length, in the place of L you have to consider LC. Then it becomes tan HMLC by MLC, and hence Q actual is equal to efficiency into Q ideal. And we have defined the effectiveness of a fin, another term, as heat transfer with fin to that of heat transfer without fin. And this you will get effectiveness root of Kp by HAC, which can be identified as 1 by square root of Biot number. Hence the effectiveness of a fin depends on the Biot number, which represents the ratio of internal resistance for conduction to that of external resistance for convection. It is HLC by K, HL by K, that's all. So where LC is volume by surface area. Now if you look at this relation, effectiveness versus Biot number, if Biot number equal to 1, effectiveness is also 1. That means there is no use of fin. Effectiveness 1 means the heat transfer with fin and without fin are equal. In that case there is no use of fin. Biot number is 1 means the value of K you have chosen is very small. Poor conducting material you have chosen, that is why Biot number has become 1. If Biot number is greater than 1, then effectiveness will become less than 1. In that case, if you add a fin, the heat transfer with fin will become less than that of heat transfer without fin. So adding a fin will decrease the rate of heat transfer. This case occurs when you choose a fin of very low thermal conducting material, or when you choose a fin under high convective heat transfer environment. If H is too high or K is too low, Biot number will tend to greater than 1 and effectiveness will become less than 1. Under such circumstances, adding fin is not desirable. If Biot number is less than 1, then effectiveness will become greater than 1, which is the most desirable case. However, effectiveness simply greater than 1 is not sufficient. For a perfect good design, the effectiveness of the fin should be more than 2.5. This is what we have seen in the other class. And now we will proceed to the problems on extended surfaces. A long copper rod having thermal conductivity 300 watt per meter Kelvin of diameter 3 centimeters is exposed to an environment at 20 degrees centigrade with a convective heat transfer coefficient of 10 watt per meter square Kelvin. One end of the rod is at 60 degrees centigrade. Calculate the heat loss from the rod and also find the temperatures at 10 centimeters, 25 centimeters from 60 degrees end. Assume it as an infinite length case. The length of the fin here is not given. We are assuming it as infinite case, but at 10 centimeters, at 25 centimeters, you are asked to determine the temperatures. Diameter of the fin is given as 3 centimeters, and hence the cross-sectional area of the fin is pi by 4 d square, and perimeter of the fin is pi d. M value, which we have assumed as root hp by ka. H is 10, perimeter is pi d, k thermal conductivity 300, area of cross section pi by 4 d square will give you 2.108 per meter. Now theta naught, the temperature difference at the base, is T naught minus T alpha, 60 minus 20 equal to 40. Therefore, you can determine the heat loss from the rod, because it is of infinite length case, using the formula square root of HPKA theta naught. H is 10, perimeter is pi d, K is 300, A is pi by 4 d square into theta naught 40 degrees. You will get 17.88 watts. Now how to find the temperatures at 10 centimeters and 25 centimeters? You have to use the temperature distribution equation for a fin of infinite length. That is T minus T alpha by T naught minus T alpha equal to e power minus mx, where T is the temperature at any location x from the face. Now we know T alpha is 20, T naught is 60, M value 2.108. By substituting different values of x in the equation, you will get the temperature at different points. So at x equal to 10 centimeters, T equal to T alpha plus e power minus mx into T naught minus T alpha 40, that is 52.39. At x equal 25 centimeters, the same expression, you will get 43.61 degrees centigrade. In the place of x, instead of 10 into 10 power minus 2, we use 25 into 10 power. So the temperature at the base is 60, at 10 centimeters is 52, at 25 centimeters is 46. So as we proceed along the length of the fin, the temperature gradually decreases, delta T goes on decreases. So convective ability of the fin also decreases as we move along the length of the fin. Maximum amount of heat it dissipates at the base, because maximum delta T will be there. As we move along the length, delta T between surface and surroundings goes on decreases, so end portion of the fin is mostly ineffective. So there is no point in using a long fin. That is what we have seen. It is always preferable to go for a short fin. Suppose you take a too short fin, imagine, very short. Then temperature may be good, it may convect more amount of heat within that small length, but the improvement in surface area becomes negligibly small. So the purpose of extension of the surface will not be served if you go for a too short fin. If you go for a too long fin, the end portion of the fin may not be able to convect heat properly. So via media we have to see, and that is why we have seen the perfect design is where the value of Mn to L should be greater than, not greater than 2.5. That care we have to take. Now let us go to the second problem. A copper fin K10 300 watt per meter Kelvin of thickness 3 mm, you can see this is the thickness, width 15 mm and length 45 mm is attached to a surface maintained at 200. If the environment is at 40 degrees centigrade with convective transfer coefficient 10 watt per meter square Kelvin, calculate the heat transfer from the fin by assuming it as number 1, infinitely long fin, number 2, its end is insulated, number 3, using general solution, and number 4, using approximate method, and compare the result. It's a very interesting problem which will include all the 4 cases we have considered, and let us see which one will give you the exact solution or correct solution. Again, I need not specify. We are assuming it as one-dimensional problem. We are considering only conduction and convection and neglecting the radiation. We are assuming steady state conduction, and we are not considering the we are not considering thermal conductivity variation with respect to temperature, and we further assume it is a uniform cross-sectional area of fin. These are the assumptions we have taken in this particular case. Now to calculate M, the most important and the first step in any fin problem is M. To calculate this M, we need HPKA, where P is the perimeter. Perimeter of the fin is 2 times W plus T, which is equal to 36 into 10 power minus 3 meters. And A, coming after K, is cross-sectional area of the fin, which is 15 into 3 into 10 power minus 6 meter square. And then tan hyperbolic ML, because you know M, you know L 45 mm, tan hyperbolic ML is also calculated because it is also a parameter of interest in calculations. You got it as 0.3172, and theta naught, temperature difference between the fin and surroundings at the base, is theta naught 200 minus 40, which is equal to 160 degrees centigrade. And now for the first case, infinitely long fin, formula to determine Q as derived earlier is square root of HPKA into theta naught. Root of H 20, perimeter 36 into 10 power minus 3, K, thermal conductivity of the fin material 300, cross-sectional area of the fin 45 and 10 power minus 6 into theta naught 160. And second case is Q equal to square root of HPKA theta naught into tan HML. Square root of HPKA into tan HML. Tan HML value is 0.3172. So this is 5 watts. 5, we will get the answer 5 watts. So perhaps this answer is 5 by 0.317. See the difference. 5 by 0.3 means roughly you will get in the first case around 15 watts. Let us check whether it is. Okay. That will come around 15 watts roughly, whereas in the second case it is giving only an answer of 5 watts. Now let us take the general solution, because this fin is not insulated at the end and this is of not infinitely long. So both answers are wrong. This, at the end of this fin, from the last element, the heat enters into the environment by means of convection. So general solution is more appropriate. So if you use the general solution, Q equal to square root of HPKA theta naught into tan hyperbolic ml plus h by mk divided by 1 plus h by mk into tan hml. That will give you the answer 5.13 watts. So in these three methods, if you see, the most accurate one is 5. By taking the fin as an approximate and insulated, you are getting 5 watts, less than 5.13, because, follow carefully, you are getting a value less than 5.13 because you are neglecting the heat transfer from this end phase. Look at the pointer here, arrow. You are neglecting the heat transfer from this end phase by considering it as insulated. So because of this, you are getting a value less than the original heat transfer of 5.13 watts. Whereas an infinitely long fin, answer is far off from reality. This is around 15 watts, which is totally wrong. Now let us see what is the advantage of going for approximate method. In the approximate method, we slightly increase this fin length. Look here at the arrow. We increase this length by delta L such that from the increased length, the rate of heat transfer into the environment is by means of convection, and that convective heat transfer is made equal to the heat transfer from the end surface. Then by increasing delta L, you can treat the end phase as insulated. Now how much you have to increase? Already we have seen cross-sectional area by perimeter, that is approximately T by 2 for a rectangular fin. So corrected length is L plus T by 2, which is equal to 46.5 into 10 power minus 3 mm. The m value remains same, root of HP by Ka. Now fin efficiency, as we have derived for a fin with end insulated, tan hyperbolic MLC by MLC, it is 96.5%. Once you know fin efficiency, Q ideal you can determine and multiply with fin efficiency, you will get Q actual. Ideal heat transfer is nothing but the maximum possible heat transfer when the entire fin is maintained at its base temperature. So HEA delta T, where H is 20, area is 2 times W plus T, this is perimeter, into length into delta T. We are not considering the end phase because that heat transfer is also included in the corrected length. So this will be around 5.368 watts. Now Q actual is equal to Q ideal into fin efficiency, 5.17 watts. So you can see now the answer Q 5.17 watts is more or less close to the general solution. Hence, an approximate method is the best method to solve the problems with negligible error. That is what we have to conclude from this problem. So this problem covers all the 4 types or cases to determine heat transfer from a fin. So let us move to one more problem. Imagine 15 number of rectangular cross-section fins are attached to a transformer base of 20 by 20 centimeter square side and maintained at 150 degrees centigrade. That means this base plate is at 150 degrees centigrade. The thickness of each fin is 2.5 mm and width of the fin is 20 centimeters. This is the width. And having a height of 2 centimeters from base, that becomes the length. L is 2, W is 20, T is 2.5. Now again, to calculate M, first we need perimeter and then we need cross-sectional area. Perimeter 2 times W plus T, that is 2 times 20 centimeters plus 0.25 centimeters into 10 power minus 2 to convert it into meters. You get 40.5 into 10 power minus 2 meters. Now M is equal to square root of H 20 perimeter by Ka. K, thermal conductivity of the film material, is given as 15 watts per meter Kelvin into 5 into 10 power minus 4. You got 32.86. And theta naught, temperature difference at the base, is 120. Cross-sectional area of the fin AC is, you can look here, heat is flowing in this direction as the arrow moves. So the cross-sectional area available for conduction heat transfer is this 20 into 2.5 in 10 power minus 5. That is 50 into 10 power minus 5. That is what we have substituted here. 5 into 10 power minus 4. 50 into 10 power minus 5 is 5 into 10 power minus 4. Now let us use the approximate method for solving this problem, and by converting this L into LC. LC is equal to L plus T by 2. By considering LC, I can now assume the end of the fin is insulated, and surface area of the fin becomes perimeter into LC. Efficiency of the fin using the formula tan hyperbolic MLC by MLC will get 86.4%. You know M, you know LC, substitute and kind tan hyperbolic, divide with MLC, 86.4%. Now Q ideal, HAS into delta T, H 20, surface area P into LC, delta T, because we are calculating ideal, I assume that entire fin is at a temperature of 150 degrees centigrade, hence delta T throughout the fin length is 120, 20.655 watts. This is ideal. Now actual heat transfer is Q ideal into efficiency of the fin, which is equal to 17.84 watts. We have 15 fins altogether. So the total heat transfer from the 15 fins is 15 into 17.84, 267.68. In addition to these fins, you have unfinned area left out. Out of 20 into 20 centimeters square, that is 400 centimeters square, fins occupy only a cross-sectional area of 15 into 10 power 5 for each fin, like that 15 fins. So still there is a bare area or unfinned area which is equal to total base area minus finned area. Total base area is 20 into 20 into 10 power 4 minus meter square, and finned area for 15 fins, each fin 20 into 0.25 into 10 power minus 4. So the remaining area is unfinned area, which is AB minus AF, convex heat as usual with a convective transfer coefficient of H, and temperature difference between surface and surroundings as 150 minus 30. That amount of area from the unfinned surface is 78 watts. Now heat transfer from 15 fins is 268, 7.68, and from unfinned area is 78. Total heat transfer is 345.68 watts. Suppose there are no fins at all, then heat transfer from the surface without fins is H 20, area 20 into 20 centimeter square into 10 power minus 4 meter square, delta T 150 minus 30, 96 watts. So by providing fins, the heat transfer from the surface is increased to 345.68 watts. Without the fins, it would have been only 96 watts. That ratio of heat transfer with the fins to that of without fins is known as effectiveness of the arrangement, which is equal to 3.6. So this is the second model. In circumferential fins or in triangular fins, the derivation theta equal to c1 e power mx plus theta c2 e power minus mx is not applicable because the cross-sectional area is continuously varying. In such a case, the problem can be solved either by invoking Bessel functions into the solution, may be difficult at undergraduate level, or by using the graphs already generated using those functional relationships. So let us see now how this graphical method is useful to determine the heat transfer. Very simple. This graph gives you directly the efficiency of the fin. So once you know the efficiency of the fin, Q actual is equal to Q ideal into efficiency. Q actual formula you can determine from the surface area multiplied with H, and considering delta T uniform throughout the length of the fin as at the base. So it is another simplest method. Now let us see how to use these graphs. This parameter on the x-axis is LC to the power 3 by 2, that is actually one L outside and one L inside. So L root HL by K. See, this root HL by K indicates byte number, one L outside. So it is something related with the parameter influencing tan HML by ML or something like that. So now 1, 2, 3, 4, 5 represents the curves for ratio R2 by R1. And similarly here also for different thickness L and for, this is for rectangular cross section and this is for triangular cross section. If R2 by R1 is 1, 2, 3, 4, 5, choose different curves. This is R2 and this is R1 from up to base, and R2 is outer radius for the circumferential fin. Now look, let us have a look at the problem. A cylinder of 2.5 centimeter dia and 0.25 meter length, the surface temperature is maintained at 170, provided with 25 number of circumferential fins equally spaced along the length of the cylinder. Circumferential fins. The fins are made up of aluminum with 1 millimeter thick and 1 centimeter height from cylinder surface. So if the surroundings are maintained at 30 with a heat transfer coefficient of 200 watt per meter square Kelvin, calculate the heat loss to the ambient and its effectiveness. Systematically, if you follow, you can solve this problem very easily, but by using graphical method, because the derivations which we have developed are not useful to solve this problem because of variable cross-sectional area. Now let us see quickly the data. The L which is indicated in this equation is R2, in the graph is R2 minus R1. So L is equal to R2 minus R1. He says 1 centimeter height from cylinder surface. That is nothing but R2 minus R1. In meters, 1 into 10 power minus 2. And LC is L plus T by 2. And mean area is R2C minus R1 into T. And R2C is again R2 plus LC. LC is L plus T by 2. And the perimeter LC root H by KAM is 0.5. Now R2 by R1 is 1.8. Now from this graph you can obtain for such readings efficiency of the fin as 0.8. Once you know R2 by R1 and LC root H by KAM, you can obtain that parameter and you will get the efficiency of the fin 0.83. The total fin surface area is 2 pi R naught square minus Ri square into 25 number of fins are there, which is equal to 550 centimeters square. and total heat transfer area available is 2 pi R0 square minus R1 square into 25 plus 2 pi R1 into L into height of the cylinder 0.25 minus 0.025, that is equal to 0.07919 meters square. Beta, the ratio of finned surface area to that of unfinned area, you will develop AF by A 0.6945. And the efficiency of the fin is tan HML by MLC, you got it as 0.83, and then area wide fin efficiency is beta eta plus 1 minus beta is 0.931. Now Q actual equal to efficiency of the fin into HEA delta T, which will give you 2064 watts. And if there are no fins on the length of the cylinder, the heat transfer without fins is 2 pi RL into H into delta T, which is equal to 550 watts. And hence the effectiveness of the arrangement is 2064 divided by 550, which will give you a value of 3.75. That is the effectiveness of the arrangement. Another important application of fins is these stiffener rods. Whenever we insert a rod as a stiffener between two, the rod will start acting as a fin, extracting heat by conduction from the end faces and delivers into the environment by means of convection. The same problem like fins. Suppose there is a 5 centimeter diameter bar of thermal conductivity 35 watt per meter Kelvin is fitted between two plates. One is maintained at 200, the other one is maintained at 100 degrees centigrade. And the length of the rod is 0.6 meters and diameter of the rod is 5 centimeters. Environment is at 30 degrees centigrade with a convective heat transfer coefficient of 20 watts per meter square Kelvin. So heat enters into this rod from this end by conduction and from this end also by conduction. It enters and leaves to the environment by means of convection. So the standard governing equation is Qx is equal to Q at x plus dx plus Q convection. That means you will get the solution theta C1 e power mx plus C2 e power minus mx. It is also a uniform cross-sectional area fin, one-dimensional conduction, radiation is neglected, thermal conductivity is treated as constant, and of course under steady state condition. So the equation for theta is C1 e power mx plus C2 e power minus mx. And m value root hp by Ka, where h is 20, perimeter is pi d into L, pi d, K is 35, area pi by 4 d square, that 4 has gone to the numerator, pi by 4 d square, diameter is 5 into 10 power minus 2 whole square, which gives you 6.76 per meter. Now the boundary conditions are to solve this equation. At x equal to 0, theta is 200 minus 30, 170. At x equal to 0.6, theta is 100 minus 30, 70. Now the equation becomes 170 equal to C1 e power mx plus C2 e power minus mx at x equal to 0, hence C1 plus C2 is 170. The other equation is 70 equal to C1 e power m into x is 0.6 at the other end plus C2 e power minus 6.76 into 0.6. By solving these two equations, you will get C1 is 1.16 and C2 is 160.83. Hence, the governing equation for temperature verification in a fin which is fitted between two plates is, in this case, is theta equal to 1.1616 e power mx minus 168.83 e power minus mx. M is constant, which is 6.76 as found earlier, and so this theta is the temperature difference at any point on this material between the surface and surroundings. So by knowing x, you can determine theta. Now let us see what is the requirement here. Determine the position of minimum temperature in the rod. Once you know temperature distribution equation, to determine the minimum temperature position, either maximum or minima, you have to find its first order derivative, equate it to 0. So d theta by dx equal to 0. You will get e power 2 mx so and so, or x is equal to 0.368 meters. That means at a distance of 36.8 centimeters from the left plate, the temperature will be minimum. Let us see what is it. Total distance is 60. So center point is 50, 30. Because 200 is here and 100 is here, the minimum temperature occurs towards 100 degrees side. That is why it is not exactly at center 30. It occurs slightly away from the center towards lower temperature side and is at 36.8 centimeters from the left plate. Now let us see, if you know the position of minimum temperature, by substituting the x equal to 0.368 in the equation, you will get the temperature distribution as 1.1616 e power so and so. By substitution, you will get theta at x equal to 0.368 is minimum and is equal to 28 degrees. That means theta is the temperature difference, and hence T, temperature at that point on the rod, x at 0.368 is equal to 30 plus 28, which is equal to 58, because theta is T0 minus T alpha. Now how to determine Q, rate of heat transfer from this rod? This rod, by taking heat from the plates into it through conduction, dissipates heat to the environment by means of convection. So best equation is Q equal to integral 0 to L HAD. HA delta T. That delta T is theta and the area of that elemental strip is perimeter into dx, where theta is again the same equation, 1.1616 e power mx 6.76x plus 168.83 power minus mx dx. You know h value, we know perimeter, and we know the integration limits 0 to L. By integrating it, you will get Q equal to root of HBKA, etc., and that amounts to 31.518 watts. So this is about the fins or extended surfaces, where we have seen all typical models problems, and by using these examples you can solve any complicated problem on fins of uniform cross-sectional area, or by using graphical method you can solve problems on circumferential fins as well as triangular fins. Most of the practical cases, no single fin will be there, will be more than one number of fin will be there, where the area wide efficiency and effectiveness of the overall arrangement plays an important role rather than a single individual fin. Now let us quickly have a look what we have covered and what we have to remember as far as these extended surfaces are concerned. Point number 1, fins are meant for increasing the surface area, thereby increasing the rate of heat transfer from the surface. Point number 2, as the end area of fin is negligibly small, a fin with insulated end case can be approximated for its analysis. The general solution for a fin of uniform cross section, of course under one-dimensional under steady state condition with constant properties, is theta equal to C1 e power mx plus C2 e power minus mx. A short fin is more efficient since the temperature gradient along its length is very low. If you take a long fin, there will be lot of variation of temperature. At the end part, it becomes very low, and hence the end part may not be able to contribute much to the heat transfer. A long fin is inefficient since the end part of it cannot contribute for heat transfer. Hence, the fin design, the ML value is restricted to 2.5 or less. Even if you look at the formula efficiency, tan HML by ML, the ML value as we go on increasing, the denominator increases, but numerator approaches 1 only, maximum is 1, irrespective of the denominator. Hence, the efficiency falls drastically low as we go on increasing the value of ML. Fins made up of high thermal conducting material exposed to low convective environment are more effective. A fin is more effective. High thermal conducting material, Biot number HL by K, K is high. Low convective, H is low, Biot number becomes very, very less than 1. When Biot number is less than 1, that fin is of more effective in nature. The effectiveness of a fin depends on Biot number. We have seen Biot number is the ratio of internal resistance offered for heat transfer, that is within the material, the conduction resistance, and to that of external resistance offered for heat transfer from the surface to the environment, that is convective resistance. So that Biot number is HLC by K, where LC is the characteristic dimension which takes care of the variation in cross-sectional area and surface area. Thermowells, that means to measure the temperature of a gas flowing inside a pipe, we construct a small well into which we insert the thermometer. That well in which we insert the thermometer and which is in turn exposed to the flowing gas is known as thermowell. The thermowell used in temperature measurement of fluid flowing in a pipe acts as a fin, and fin resulting in giving more error in measurement. So you can calculate by means of by considering that thermowell as a fin of hollow cylinder, you can calculate what will be the temperature at the end, whether it is giving exact value or some error is involved in it. Generally, some error is involved because that well acts as a fin. That's all about the